Welcome to Mark's Tech Talk. This video is going to discuss three-phase power, and if you haven't already done so, there is an earlier video out there that introduces three-phase. So this is really part 2. So if you haven't already checked it out, check out part 1. All right, let's move on from what we've covered in part 1 and discuss something called the phase sequence. The phase sequence in three-phase power is the order in which each of the phases produce their voltage and when they reach their peak. So in other words, if the A phase reaches its peak first, and then the B, and then lastly the C, we call that ABC phase sequence. And ABC phase sequence is also known as a positive phase sequence. Now, if you were to start counting time a little bit later and count it right when B reaches its peak, then B would be the first, and then C, and then A would be last. That's the same order, it's just starting at a different point. So that is also referred to as a positive phase sequence. Likewise, if we started counting our time when C was reaching its peak, it would go CAB, and that is a positive phase sequence. So ABC, BCA, and CAB are all positive phase sequence. We'll contrast that with if A reaches its peak first, and then C was next, and B was last, that's the ACB sequence, and that's called the negative phase sequence. And likewise, if we start counting that at a different time, we could have CBA or BAC. Those are all referred to as a negative phase sequence. And these are important because they determine the direction of rotation for a three-phase motor. And if by chance you're in a situation where you're hooking up a motor and you first turn it on and it's turning in the reverse direction, all you have to do is reverse any two of the leads, and that will make it change direction into the correct rotation. So reversing any two leads will give it the opposite phase sequence and therefore the opposite direction of rotation. Another thing to be aware of is how do transformers work in a three-phase circuit? Well, it turns out it's actually pretty straightforward. Essentially, all we do is use three one-phase transformers, but like the sources and the loads, we can hook up the primary and secondary of the transformers in either a star or a delta. And remember, star and Y are the same thing. So here is a YY configuration of transformers. Remember Y, they're all going to meet at the neutral. So looking at the black leads, which is the primary, they all meet at this neutral, and you have one connection to each of the windings, each of the primary windings coming from that neutral. And then the opposite end of each of these windings goes out to each phase. So here's the opposite end, goes to C, here's the opposite end, goes to A. We can do the same thing on the secondary. We have this common point, the neutral goes to this winding, goes up to this winding, and it reaches this winding. So three windings all meet at a common point, and the opposite side of each winding goes out to one of the phases. Okay, so this is a YY configuration. We can have a Y delta. Here the primaries are wired exactly the same as we had a moment ago, but the deltas are in the secondary. And what that means is each of the windings connects to another winding on both ends. So it forms a circle. So you can kind of go from one winding to another to another. So if we start out on this bottom winding, we go through the winding, come up to a phase, phase A, go through the next winding, come out to a phase, go through the next winding, come out to a phase, and that would be back to where we began. So essentially you have a big circle here. You can go through all three windings when you're drawing this out without lifting your pencil. There is no common point here. You're just connecting one end of one winding to the end of the next winding, going around in a big circle. That is a delta configuration. Here's a delta-delta. We connected the primary to a delta configuration. See, there is no neutral here. And if we wind our way around, we start at the bottom here, go through the winding, and then we go up through the second transformer winding and through the third, and then come back down to where we started from. And wherever you connect between two windings, that's a phase connection. There's a connection between two windings here. There's a phase connection. So this is a delta-delta wiring configuration for transformers. Likewise, we can have a delta Y. Here is a wattmeter. This is how we measure power in an AC circuit, or a DC for that matter. It's a special meter that actually has two coils in it, one of which is meant to measure the current and one of which is meant to measure the voltage. And remember that the power is the product of voltage times current. So what happens is when this meter measures the current in the series coil and the voltage in the parallel coil, internally it multiplies those together to give you a power indication on the outside of the meter, the meter scale, essentially as a product of that voltage and the current. And that's how a voltmeter works. Now, there is two separate coils here, and some voltmeters will bring both coils out separately, and they'll actually have four terminals, two terminals for each of the coils. Other ones will recognize the way you usually hook this up, the two coils have a common point here and you tie them together. So they actually tie these together internally, so you actually have three terminals, one on one end of the current coil, one on one end of the voltage coil, and then the common point between the coils is another terminal. So a wattmeter might have 3 or 4 terminals, but they all work the same way. You have a current coil and a voltage coil, and the product of those readings is what's displayed on the outside of the meter. So the question now becomes, how do you measure three-phase power? With three-phase power, we're going to take this idea of a wattmeter with a current coil and a voltage coil and essentially just do the same thing 3 times. So with our meter, we're going to duplicate this wiring 3 different times for 3 phases. So we'll have something like this. This is a YY configuration, Y source, Y load, and we're going to measure the power in each of the phases. So we have the wattmeter in series here. The current coil, the wattmeter is in series, and the voltage coil is measuring from that phase to the neutral. And we do the same thing with the other 2 phases. One part's in series and the voltage is in parallel. And in series here, and the voltage is in parallel. And the total power would simply be the sum of the 3 wattmeters. If you just add up the readings of the 3 meters, that would be the total power in the 3-phase system. But we have a little problem here, and that problem is that neutral is not always present. Think of the delta configuration. You don't have access to a neutral in a delta configuration. So how do you measure power? Well, let's investigate this a little further. We're going to look some more at this YY and change this around just a little bit. So we're going to take 3 wattmeters and we're going to change the wiring just a bit so that we use a different voltage reference point. We're all going to tie all 3 meters to the same point, but that point is going to differ from the neutral by some voltage. And I've shown that as a DC voltage. It might be DC, or more likely it's AC. It doesn't really matter. The point is, it's some voltage different than the neutral voltage. So what happens here? Well, now this wattmeter is probably reading a little bit less because it's reading presumably less voltage than it did before. So the product would be less and this would read lower. On the other hand, these 2 wattmeters have a higher voltage than they did before because, again, this is shifted upward from the neutral. So this is reading higher and this is reading higher. And I'm not going to prove it, but it turns out that the amount that these 2 read higher is equal to the amount that this reads lower. So the sum of all 3 of these remains the same, even though we shifted this voltage reference. Nothing really changes there, at least in terms of the sum of the 3 meters. So we're still going to get total power. Now, it turns out we can actually take that to the extreme and make that common connection actually equal the voltage on one of the phases. So now we have a lot more voltage on this one and a lot more voltage on this one, but this one, since this voltage, this reference voltage, is actually the phase voltage, the meter, the voltage coil on this wattmeter will actually read 0. And if that voltage is 0, then that meter is going to read 0 because 0 times anything is 0. So if that's reading 0, we really don't need that meter. And we can actually eliminate that meter. And if we take that out, now we're reading the total power in a three-phase circuit with only 2 meters. So this is how you can hook up the three-phase using 2 meters. Now the interesting part of that is that you're no longer using the neutral, and therefore you're able to measure total power in a delta system. It also has the advantage that power company only has to provide 2 meters to read three-phase power to a customer. And in reality, what they will do is they'll take both of those meters and they'll put them in the same case, and they'll actually add them together internally so that the meter reader doesn't have to do the addition and potentially make a mistake there. They actually have the instruments all built into 1 meter. All right, so essentially that 1 meter is really 2 watt meters in the same case, and that is reading the total power for your three-phase load. All right, so hopefully that gives you a little bit more information about three-phase, and particularly how to measure power and what phase sequence is and transformers and so forth. Hope you enjoyed this, and stay tuned for more.